Okay, I'm going to do one last one of these to finish off this chapter. And the reason I picked this problem is because this is from your textbook. It's number 58, and it is a 3-dot problem. So it means it's supposed to be very difficult. And the reason I picked this one is because really it's just the exact same thing like I already showed you. So the goal here is to use conservation of angular momentum to figure out how fast something is going is after a collision. Okay, so if the I omega could be one way we calculate it, r cross p is the other way we calculate it. So in this case we have this disc, this merry-go-round with a child on it. The child's going to catch a ball. Okay, so let's go ahead and calculate angular momentums before. So the disc and the child, they are stationary, which means that their angular momentum before is 0. So the only thing with angular momentum before is the ball. And for the ball, we can use r cross p. Okay? Then after, the ball, the child, and the merry-go-round are all traveling with the same angular velocity, so we can add up all their moments of inertia. So for the merry-go-round, the child, the ball, and this would be times their final angular velocity. Okay, so for the ball, it has a mass of 1 kilogram, it's a heavy ball. Okay, it has a velocity of 12 meters per second. Okay, and the radius, this distance here, is 2 meters. Now we need the component of this velocity that's going to be perpendicular, so this one right here, which, if this angle is 37 degrees, that's going to be v cosine 37. So we're going to have the radius times the velocity times the mass. Here, let's redo that order. So the radius times the mass times the velocity times cosine of 37 is equal to moment of inertia of the merry-go-round is 150. Moment of inertia of the child, we would treat the child as a point, so that would be 30 times r squared. And we do the same thing for the ball, so that would be 1 kilogram times r squared times r omega final. Okay? This should be equal sign right there. So let's go ahead and substitute in some values. R is equal to 2 meters. Mass of the ball is 1 kilogram. Velocity of the ball is 12 meters per second. Okay? Let me punch in my calculator. Okay, so on the left we get 19.2 kilogram meters squared per second. On the right we have 150 plus 30 times 2 squared, so 30 times 4, or 120 from the child, and then 1 times r squared, or 4 from the ball, okay, is times omega final. Okay, so that gives us 274 omega final, 19.2 kilogram meters squared per second. This is the moment of inertia, so it's kilogram meters squared. Okay, so we divide by 274 and get a final angular velocity of about 0.07 radians per second for the merry-go-round. Okay, and if we wanted to, we could find out how fast the child would be moving if we multiply this by the radius of 2 meters. Okay, that would mean the child has a velocity of 0.14 meters per second. We can take another step, find summation of the acceleration, what the child feels, so omega squared r, and that would be about 0.01 meters per second squared. So very small acceleration, very slow rotation. Okay, and that is a 3-dot problem from the book. It's just the same exact thing. Conservation of angular momentum, okay? It can get confusing because of all the calculations you have to do, but at the end of the day, it's very simple, okay? Angular momentum of a system before and after will stay the same unless some external torque acts, okay? For this merry-go-round, it experiences an external torque from the ball, causing its angular momentum to increase. The ball experiences a net torque external to it from the child in the merry-go-round, causing its angular momentum to decrease. Combined, we have a net gain of angular momentum of 0.